Welcome to The Explainer. Today, we're going to pull back the curtain on the websites and apps you use every single day. We're going to break down the 15 fundamental building blocks that make all of modern system design actually possible. So, have you ever stopped to wonder how a service like YouTube or Netflix can possibly handle millions of people all at once without just collapsing? Well, it's not magic, I promise. It's actually a really clever architecture of all these cooperating parts, and we're about to map the whole thing out. So here's how we're going to do it. We'll follow the journey of a single request through 4 key stages. First, getting into the system, then processing that request, then how it handles data and speed, and finally, how the whole thing scales up for millions of users. Okay, first up, entering the system. Before your request can even be processed, it has to navigate the entire internet to find the right front door, and then, actually be allowed inside. It all starts with DNS, the domain name system. See, when you type in youtube.com, you're using a name that we humans can remember. DNS is basically the internet's phone book. It translates that easy-to-remember name into a numerical IP address that computers need to find each other. So once your request finds the right address, it runs into the load balancer. This thing is the system's traffic hub. It stops any one server from getting totally overwhelmed by smartly spreading all the incoming requests across a whole fleet of servers. This is exactly how shopping sites manage to survive massive holiday sales. Next, that request arrives at the API gateway. You can think of this as the system's secure front door. It really acts like a gatekeeper, making sure every request is valid, checking for permissions, and then pointing it to the exact internal service that can handle the job. So let's just recap that first leg of the journey, right? DNS finds the right house, the load balancer picks an open door, and the API gateway checks your ID. And just like that, your request is safely inside the system. Okay, the request is in. So what now? Let's take a look at how the system's brain actually processes it. This is where the real work gets done. This internal communication all happens through APIs, application programming interfaces. They basically provide a clear set of rules for how different software components can talk to each other. It's kind of like a restaurant menu. You know exactly what you can order and how to ask for it, which creates a really nice standardized conversation. A lot of modern systems are built using microservices. So instead of one giant program trying to do everything, the application is broken up into a team of specialists. One service might handle user profiles, another handles payments, and a third handles recommendations. Yeah, it adds some complexity, but the trade-off is this massive flexibility and the power to scale each part on its own. But what happens if one of those specialist services is busy? Well, that's where a message queue comes in handy. It's basically the system's shared to-do list. One service can just drop off a task, like send a confirmation email, and then immediately move on to the next thing. Later, another service that's free can pick up that task and finish it. This prevents bottlenecks and keeps the whole system running smoothly. Processing a request almost always involves data. So the next big question is, how do systems store all that information and then get it back to you, the user, as fast as humanly possible? The heart of data management is, of course, the database. This is the system's long-term memory. It is the single source of truth for literally everything, from user accounts and passwords to product inventories and order histories. But here's the thing. Databases aren't always the fastest. For pure, raw speed, systems use a cache. This is a layer of super fast, short-term memory that stores copies of data that gets used all the time. The next time your profile picture loads in the blink of an eye, you can probably thank a cache for that. So the key difference here is really speed versus safety. A cache is all about speed for temporary data, while a database is all about the permanent, safe storage of that data. They really work together as a team to give you the best of both worlds. Now, to get content to a global audience really quickly, systems use a CDN, or a content delivery network. This is a network of servers spread all across the world that store copies of files like images and videos. So a user in Japan gets the file from a nearby server in Asia, not all the way from the US, which, as you can imagine, dramatically cuts down on loading times. And for those huge files, systems rely on object storage. Think of it like a massive warehouse. It's not meant for nicely organized, structured data like a database is, but it's absolutely perfect for storing enormous individual things like user-uploaded videos, photos, and system backups. So we have all these components, but how do they work together to handle a massive scale? Let's get into the final set of tools that allow a system to grow from 100 users to millions, and seemingly without breaking a sweat. A key technique here is replication, which is just a fancy way of saying making safety copies of your data. If a primary database fails for some reason, a duplicate replica can take over instantly. This gives you fault tolerance, and honestly, most of the time, the user won't even notice a thing. But what happens when the data gets so big that it can't even fit on a single powerful machine? That's where sharding comes into play. This technique splits one huge database into smaller, much more manageable pieces called shards. So to increase capacity, you just add another shard, which lets the database scale almost infinitely. To protect itself from getting just completely overwhelmed, a system uses a rate limiter. This is the system's bouncer. It controls how many requests a single user can make in a given amount of time. This prevents abuse and makes sure the system stays stable and fair for everybody. And finally, how do engineers know if anything is going wrong? With a monitoring system. This is basically the system's dashboard of vital signs. It's constantly tracking performance, memory usage, and error rates, acting as an early warning system to flag problems, often before users are even aware of them. So when you put it all together, these 15 building blocks all serve three critical goals. They make a system fast, using things like caches and CDNs. They make it reliable with replication and monitoring. And they make it scalable, using load balancers and sharding to handle massive growth. So there you have it, the blueprint of the modern internet, from the front door all the way down to the deepest storage. These are the fundamental ideas that power our digital world. So the only question left is, now that you know the building blocks, what would you build?